So in this lesson, we're going to be talking about arcs and chords, which are other parts of circles that we want to be comfortable with because we'll be looking at theorems and relationships with using arcs and chords later on, as well as formulas. So the first thing we want to talk about is what is a central angle. And we actually talked about a central angle before when we did regular polygons, but a central angle is basically an angle where with a vertex at the center of a circle. So if we look at the diagram here on the right, we can see that B is the center of the circle. So this angle ABC, or if you want to call it CBA, is a central angle. So angle ABC is a central angle. Okay. And then you can see that this is an angle, so it has a measurement, and we can see, oh, this angle measures x degrees. So the measure of angle ABC equals x degrees. Okay? So each central angle creates a corresponding arc that kind of cuts out from a circle. And we have two types of arcs. The first we're going to talk about is called a minor arc. So what I'm saying here is if you look at angle ABC, if you take a look at this and think about this as a piece of a pie, it's cutting this red part of that circumference out of the circle. And this is what we call a minor arc. All right, so think about it as minor because it's going to be kind of the smaller slice. It's between the two legs, so you can see how the arc I highlighted goes from A to C. It's in between the two legs, those two segments, the rays of your angle. So for example, we have an arc that goes from A to C. So how do we name this? How do we write the notation? We're going to use those two endpoints that go along the circle, but instead of calling it a segment because it's not straight, we're going to draw a little arc above it to represent, okay, that's an arc AC. Okay, the arc has a corresponding measure, and what's interesting and what's neat about this is that the arc, and when we write the measure of the arc, we put a little m in front, just like an angle, the measurement is going to match the central angle measure. So this arc here also measures x degrees. So arc measure equals the central angle measure. And arc measure, when we talk about this, it's in degrees as well because we're thinking how many degrees we're moving around the circle. All right, so the last thing we need to talk about is, well, there's this remaining part of the circle that we didn't look at. What do we do if we go from A to C but going to the left and we have this huge part of the circumference? Well, we call that a major arc. So basically, you're going to go around that central angle to kind of finish off that circumference. So you can see how that red arc that I drew connected to the orange minor arc creates a full circle. So typically, a major arc is going to be pretty big. It's going to be over 180 degrees. And with a major arc, we have an issue because you might be thinking, wait a minute, Ms. Huang, A and C are the endpoints of the minor arc we talked about, okay, but A and C are also the endpoints of the major arc, so can we still call this arc AC? And the answer is no, because there are two different arcs. So what we need when we write, or when we name a major arc, or basically another arc that has the same endpoints as an existing arc, is we need a third point. So let's say we have point D right here. Then we can say this arc starts at A, goes through D, and ends at C. So we'll call this arc ADC. So you can always do that to differentiate between another arc that has the same endpoints. And this also has a measurement, right? Because all arcs do measure some degree from 0 to 360. And what's cool about this case, when we have just one minor arc and its corresponding major arc, is we notice, wait a minute, it adds up to 360, so this will be 360 minus x degrees. And it really doesn't matter how many arcs you break up a circle into, they always will add up to 360 because a circle is always going to be a full 360. So that's just some vocabulary about arcs and their corresponding angles. So now we can talk about some relationships. So the first theorem, or actually the first postulate we're going to talk about, is going to be very familiar. This is called the arc addition postulate, very similar to the segment addition postulate and the angle addition postulate. So just like the other addition postulates we've talked about, here the arc addition postulate says that the measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. So basically, if you have arcs next to each other, we can add them together to get the measure of a larger arc. So for example, if you look at this diagram on the right, we've got AB and it's adjacent, which is right next to BC. So we can say, hey, if I add together AB and BC, then together they are going to give me the overall measure of the arc from A all the way to C, right? And we can, of course, add more arcs together, so it doesn't have to be limited to two, because any two will add up to a larger one. But anyway, we can just add adjacent arcs to create a larger arc. So this is saying if I wanted to know the measure of arc A to C, if I just add together the two smaller pieces that are adjacent right next to each other, AB and BC, I'm going to get that larger arc in blue, right? So then if we take a look at example 1, I'm looking for the measure of an arc, BD. So what I want to do is I want to make sure I have arc measure. So remember, by the definition of an arc measure, we can take a look at the diagram and say, wait, there's no arc measures, right? I don't see anything along the circumference, but I do have central angles because this F is the center. So what I can remember is, wait, definition of arc measure tells me that the arc measure is equal to the central angle measure. So that means this A to E is 97.4 degrees, this E to D is 52 degrees, and etc. So if I'm looking for the measure of arc BD, I can say, okay, well, what's the central angle that intercepts or creates the arc BD? Well, BD is this arc, so I would be looking at this central angle. So you can kind of look at that relationship and either find the measures of the angles and then find the corresponding arcs, or take the angles like I did, bump it out to the arcs, and just work with the arcs. So again, totally up to you, okay? But there's a lot we can look at here. So you might be thinking about, all right, so I know the relationship between arcs and angles, Ms. Huang, but how do I actually find BD? Well, that's where we have to go back and look at other relationships, right? So you might be thinking, okay, well, arc BD is equal to the sum of arc BC and arc DC, right? This is my arc addition postulate. And then I'm thinking, all right, but I don't know the measure of BC or DC. But wait a minute. I see something very familiar. Let's just take out these two angles, AFE and BFC. If this is 97.4 here on the left, and this is an intersection, we've got vertical angles. And we know vertical angles are always congruent. So then I know the measure of angle BFC is equal to 97.4. And what do you know? The measure of arc BC is equal to the measure of angle BFC because of my definition of an arc measure. So we know that arc BC is 97.4. So we're halfway there. So all I really have left is to find the measure of arc DC. So now if I look back at my diagram and say, okay, well, where is this DC? Well, something I might realize, and I'm just going to erase what I've kind of drawn over here, just to give you a clean slate. I might realize, hey, here's DC. And I know information about AE and DE. And if I look at that, wait, by putting those two arcs together, that large one in red from A to D and then CD, I'll realize, hey, that's half a circle. What do we know about half a circle? Half a circle is 180. So know the measure of arc AD plus the measure of arc DC has to add up to 180. And again, by our arc addition postulate, AD is just the sum of AE plus ED. And then we know from earlier, right, AE E is 97.4 because it equals its central angle. We know DE is 52, and now we have an equation we can 100% solve, right? So putting it together, we will see, right, that the measure of DC, I'll just skip some work here to save you a little bit of time, is equal to 30.6 degrees. Right, so now I have my two missing pieces. I can finish this off. So the measure of arc BD equals 97.4 plus 30.6, which gives me 128 degrees. Is this the only way to solve it? No, you can definitely use other relationships. I've seen people say, wait, can't I also just notice that AB plus BC is 180 and use that in that way? Or can I use AE plus AB equals 180 and use that in some way too? Yes, there's lots of relationships you can use. This is just one way to get 128. Okay, so we've got some more theorems we need to talk about. And these kind of put together arcs, chords, and central angles. So remember, chords we talked about in the last lesson. Chords are these segments that kind of connect to any 2 points on the circumference of a circle, and they often do what we call subtend an angle, a central angle, or an arc. So that just means it shares the same endpoints as an arc, which also happens to coincide with the kind of intersections of the rays of the legs of your angle, right, with the arc. So you'll see that word subtend sometimes. But here we've basically got three relationships we want to talk about. And all of these start off with talking about a single circle or two congruent circles. So it's okay to have two congruent circles. These theorems will also work. What matters is that your radius is the same. That's what makes a circle congruent, right? And it could also be a single circle because all radii are the same there. So the first thing we have to say here is if we have congruent central angles, then they have congruent chords. And that kind of makes sense because if we have two congruent central angles or three congruent central angles or however many congruent central angles you want, the width of the angle, right, how far apart the legs are, will always be the same. And that distance is the chord. So for example here, if we know that the measure, that the central angles, angle EAD is congruent to angle BAC, those are congruent central angles, then their chords are congruent. So ED, which subtends or kind of connects the two legs of angle EAD, right, is going to be congruent to BC. That's what that's saying. Congruent central angles have congruent chords. Okay, the next one says congruent chords have congruent arcs. And this also kind of makes sense. If we already know our congruent central angles have congruent chords, the chords are then going to have congruent arcs because it's going to cut the same size or the same bit of the circumference off of your circle. So here, for example, if we know that ED is congruent to BC, then we can say that the arc ED is congruent to the arc BC. All right, no, that's an E, sorry, that's a little hard to read. And the final theorem we're going to talk about here tells that congruent arcs have congruent central angles. And this one just kind of makes sense because we know by definition of arc measure, the arc measure is going to equal the central angle. So if our arcs are equal, our central angles are equal. So here, for example, if we know that the arcs ED and BC are congruent, then we know that their central angle measures, angle EAD and angle BAC, are congruent. All right, so these are all theorems that you could prove, and something to keep in mind, right? Little details, right? If we're talking about congruence, you might need to do things like definition of congruence to get equality and things like that. Also notice we've got triangles. If you could look at the two legs of your angle plus the chord, we create triangles, and that could be useful. So we can do things like SAS, CP, CTC to help us prove congruent parts. All right, let's move on to some examples and kind of finish off what we're doing here with arcs and chords today. All right, so if you look at example 2a, we're looking for the measure of the arc, WS, and as always, look at what the diagram tells you. So it's telling you, hey, we've got congruent chords, right? We've got these marks. TV is congruent to SW, these chords. So what does that lead us to conclude? Well, if we have congruent chords, right, this is given, then we can say, well, my arcs are also congruent. So TV has got to be congruent to SW, right? Because congruent chords have congruent arcs, right? There's no kind of nice name for that theorem, so you just be kind of writing that out. So that's what I'm thinking in my head, and that sets up my work, because then I can use my definition of congruence to create an equation to solve. So why don't we go ahead and finish that off? 9n minus 11 equals 7n plus 11, right? Do your inverse operations. 2n equals 22, n equals 11. And then we want the measure of WS, which is 7 times 11 plus 11, or 88 degrees. Remember, you can always check by plugging that 11 back into TV as well, because our arcs should be congruent. Okay, take a look at part B. Think about this on your own for a minute. Think about how you want to set up that equation. Think about what the diagram gives you. Okay, so remember those theorems we talked about earlier work with congruent circles. It doesn't have to just be one circle. So in these two circles, C and J, GCD is congruent to NJM. And what are these? These are central angles, because you can see the vertex is at the center C, the vertex is at the center J. We're looking for the measure of a chord, right? So if we have congruent central angles, we know we have congruent chords. So we can jump right into that equation. 14t minus 26 equals 5t plus 1. I don't have a lot of space to write down my reasoning, but I really hope you guys thought about that. Why am I able to do this? Because dg is congruent to nm. Why are dg congruent to mn? Because our central angles GCD and NJM are congruent, and congruent central angles have congruent chords. These chords connect kind of the rays of the angle. They subtend the angle, they subtend the arc. So that's that connection. All right, and then we just solve this just like a plain old algebra equation, right? 9t equals 27 to get t equals 3, and nm is just 5 times 3 plus 1, or 16. So as always, like I said before, the most important part is to get the equation down right. Okay, last two theorems and one last example. So these are additional theorems that now deal with, you'll notice, a chord and a radius if you look at that diagram. So what does our first theorem say? It says that if a radius, or by extension a diameter, because remember radius is half a diameter, is perpendicular to a chord, then it bisects the chord and also the arc. All right, so if you see, for example, we're given that CD, which is a radius because we can see C is the center, is perpendicular to some chord EF, then we can conclude two things: that CD bisects the chord EF, and then by extension that's saying if we have a point here, let's call this X, EX and FX are congruent by the definition of bisector, right? So we can add that in. So that's one thing we know. And then we also know that CD is going to bisect the arc EF. So that's now telling us the arcs ED and FD are congruent by definition of bisector. All right, and this is something you can think about doing and proving with potentially triangles. If you add in CE and CF as radii, you can play with that. But anyway, that's just something to think about. Okay. Then the second theorem is related to this. It kind of goes backwards. It says the perpendicular bisector of a chord is a radius, or by extension a diameter, of a circle. So not quite the converse, but basically telling us we can have a we can figure out what is a diameter or a radius of a circle by looking for a perpendicular relationship. So if we kind of go back to that same diagram, let's say we have a circle C, right? And now what we know is that CD is a perpendicular bisector. And actually, let me change this up a bit. We won't actually know C is the center. So I'm going to just erase that dot. So all we'll know is that some segment CD, right, is a perpendicular bisector of a chord EF. What this does is this now allows us to say, hey, well, CD, whatever part of that, whatever segment that is, it's lying on a radius or a diameter of the circle. Okay, so if we're given that CD is the perpendicular bisector of EF, then we can conclude that CD lies on a radius or a diameter of the circle. Right? We don't necessarily know C is the center unless we had some more information, but we do know if I extend DC all the way to the other side, I'm going to create a diameter. So that's kind of basically it. One last example, and we're all good. So this last example, we want to find the length of NP. So NP is the length of the chord. And we might think, okay, how the heck do we do that with the information? Because all we know is RS and SM and this right angle, nothing else, no arcs, right? No NS. So we have to think, great. Well, it's still doable because I know additional information, right? So don't always just look for things at face value, kind of dig a little deeper. We know that RM is a radius. We know that RM equals 8 plus 9 or 17 using our segment addition postulate. And I'm not writing down all my reasoning, so you guys can go ahead and do that if you'd like, just to get used to, right, explaining your work. Then I can also remember for any circle, I can connect the center R to any point to create another radius. So I can say, hey, Rn is also a radius. And remember, all radii are congruent, because that's a definition of a circle, right? All points on the circle are equidistant to the center. So Rn is also 17 because all radii are the same. Why do I care about this? Well, I know that Rm is perpendicular to NP, which tells me that angle RSN is a right angle. Why is that important? Because I can create a right triangle. RSN. That's 17, this is 8. And how do we find NS? Pythagorean theorem. NS squared plus 8 squared equals 17 squared. Right? So doing all that work, we'll find NS is actually equal to 15. How does NS help me find NP? Well, remember, if we know RM is perpendicular to NP, then we know that RM bisects both the chord and the arc. And we don't care about the arc today, so I'm not going to write in the arc NP, but I know it's going to bisect the segment NP, the chord. So that means NP is basically cut in half. So NP is going to be equal to NS plus SP. And we know that NS is congruent to SP by the definition of a bisector. Right? So this is pretty much it. All we're going to do is do 15 plus 15 because SP is 15 and S is 15, NP is 30. Right? So a lot of connections we can make, and that's what's really important, is don't just think about, okay, it's a circle, so let me only think about circles. We have triangles, we have segments, we have angles, and we want to use all of those relationships that we know and are familiar with. That'll help us do the problems. All right, so that is it for this section. Please let me know if you have any questions.